that you mute yourselves for the duration of the lecture, and we encourage you to ask questions during the lectures, but please do so in the chat. And one of the organizers will communicate your questions to the instructor. And then, of course, you'll have questions to ask, the opportunity to ask questions verbally at the end. With that being said, we're very happy to welcome Eduardo Oregón-Reyes back for a second lecture on cubulated groups and virtual specialness.
Okay, thanks, Rolly, and thanks to all of you for being here again. So this is the second lecture about cubulated groups and virtual specialness. So some remind of what we did last time. So in the first lecture, what we did was just to define some of the objects of all of these, theory. That means non-positively cube complexes, cut-zero cube complexes, cubulated groups, because we want to work with groups, and we saw some examples too, and we kind of defined one of the tools or consequences of this combinatorial definition that are relevant for all of these, which are the walls and also the convex subgroups. And today we want to play with these objects a little more, but before that we will start to talk about separability and visual finiteness, which is a notion in principle not related to cubulability. After that, we will define the main topic for this mini course, which are special cube complexes and special groups. And we will combine these two notions at the end when we talk about the canonical completion and canonical reduction. Okay, and some references for today. So again, Hagwell and Weiss' original paper for special cube complexes. I think the proof and the proofs related to the canonical completion, reduction, and transparent there. The notation is not that good, but the construction is very explicit. Also, I think it's not too bad to do some self-publicity. So here, there is an appendix for also related to canonical completion and reduction, and in particular, a new contribution here is related to functoriality of this construction. And also, in case you want to learn more about this, but you don't want to see all the details, there's we have the Eagle's notes from the ICM, in which we see some perspective of special cube complexes in terms of the applications, rather than in terms of the just doing the hard work. Okay, so that being said, let's start with separability. So separability is a property for subsets of a given group. So if you have a group, we have a subset, and this subset is separable if for any A in G but not in S, there is a finite quotient. That means we have a homomorphism from G onto a finite group such that the image of this element A is not in the image of this set S. And this should hold for any A, and for any A, we should be able to find such a finite quotient. And here, the standard notation is saying that A is separated from S in the quotient F. Okay, so this is a definition for a subset of a group, but in the particular case that this subset is a subgroup, we have a nicer characterization. So a subgroup is separable if and only if H is intersection of finite index subgroups. And in case you are not interested in subgroups, but just in the group itself, you can say that the group is reasonably finite, and we denote this as Rf, in case the identity or the trivial group is separable. So this means that the trivial group is the intersection of all finite index subgroups. This is one way, and another equivalent way is saying that for any non-trivial element in our group, there is a finite index subgroup not containing that element. Okay, all of this is equivalent. And I mean, at first, this definition might seem mysterious. So for the moment, we just say that this definition, I mean, maybe the existence of a lot of separable subgroups or being reducibly finite implies that we have lots and lots of finite index subgroups. So being reducibly finite implies we have lots and lots of finite index subgroups. I mean, in case the group is infinite. I mean, if the group is finite, I mean, this means that. I mean, this definition is meaningful for infinite groups. Even though, in case you are not happy with this, there is a topological interpretation of this, which is given by Scott's criterion. So now, for this, we must look at these groups as fundamental group of topological spaces. So now G is the fundamental group of X. And for H a subgroup, we take the corresponding covering, which might be an infinite cover in general. And we say that this subgroup is separable if for any Y in XH compact. That means we have Y here. And since this is a covering, this induces an immersion. So this is an immersion. And the point is that we can promote this immersion to an embedding in a finite GT covers. So we can find a finite cover. So that this is an intermediate cover. And now we have this, and this is finite. And the point is that this immersion here will lead to an embedding in the new cover. And the moral here is that having several subgroups implies that we can promote immersions to embeddings in finite covers. So this property is actually useful in this sense because for topological reasons in general, we can produce immersions. In general, if you have, I mean, topological spaces that are Eilenberg-McLean spaces, it's not too hard to produce topological maps from homomorphisms of groups, but to produce, I mean, but to get those maps to be embeddings, that means have a real topological meaning, it's in general difficult. And this is the condition guaranteeing that, which at the end is an algebraic condition. In any case, we have this topological criterion, but for the first half, we just be happy with the algebraic characterization of separability. We'll be back to the criterion at the end when we combine all of this with this theory of cubulated groups. But now what we should see, we should go to examples of residual finiteness and separability. So the first examples, okay, I will omit all the trivial examples. That means you should assume that, I mean, finite groups are residually finite, but they are boring. So the first interesting group that is residually finite are the integers. Well, maybe for you it's also boring, but this is a good example. And the reason is that now we can describe the trivial group as the intersection of all the ideals or prime ideals. All of these are finite index subgroups. And we can consider even just the prime ideals. And for similar reasons, have that z to the n is residually finite. And we can do the same for finally generated nilpotent groups. An interesting example that is also residually finite is SL and Z. And the way to see this is that we can describe here the trigger group as the intersection of a lot of kernels, and the kernels are given by just seeing the matrices mod B. And this is for all people. So these maps are surjections, these groups are finite, so that means these are finite index subgroups of our original group. And the point is that, I mean, this is kind of a simple proof, but the point is that if we know more algebra, then this same procedure allows us to get a bunch of residually finite groups, and this is Malsiv's criterion. So each time we have a group that is finally generated, and essentially we can do the same trick in the sense that G is a subset of SL and K for K field of zero characteristic. Then we get that G is residually finite. Okay, and the proof, I mean, relies on knowing a lot of algebra, but essentially the idea is we want to use the algebra to get into this situation. And from this, I mean, each time you have a linear group, you get residual finiteness, and this is good because there are a lot of groups that we know that are known to be linear. An example are free group, and also surface groups. I mean, all of these are Fuchsian groups. Of course, we have lattices. And an example that is not that obvious is that of right-angled Artin groups. Those groups are also linear. So all these groups are residually finite, but in case you are not happy with this proof that racks are residually finite, we will see another proof later. So don't worry about this. So you can assume you don't know that racks are linear, that's fine. But in any case, this criterion is nice as long as you know that the group is linear, but I mean, there's no nice criterion for linearity. So at the end, and indeed there are interesting groups that are known, there will be non-linear, and there are interesting groups that for which the question of linearity is still open. So another examples not related to Malsev's criterion. So Hempel using geometrization proved that pre-manifold groups are residually finite. Okay, and in this, there are still some pre-manifold groups for which we don't know if those groups are linear. Another examples are out Fn. So these groups for the appropriate rank are known not to be linear, but they are still residually finite. And also mapping class groups. These are also residually finite, and I'm almost sure that the question of whether these groups are linear is still open. Well, these groups are residually finite, but maybe at this point you're wondering, is every group residually finite? And all this theory is kind of useless, and the answer is no. I mean, there are groups that are non-residually finite, and the simplest example that I know is this bounce accelerator group. And so the presentation is like this. So this group is not retrievally finite. And the proof is not at all tricky, but I don't have time to tell the proof. But the point is that this group is not Hopfian. That means that we can construct an epimorphism that is not an isomorphism. And I mean, I'll put it in the exercises that retrievally finite implies being Hopfian.
Do we understand, like, right, do we understand what is the intersection of all finite index subgroups of BSL23? We know it's not the identity, but do we know what it is?
Oh, that's a good question. I have no idea. I mean, because the proof I see is usually that by seeing that this is not Hopfian, but not being Hopfian doesn't require to compute the identity of all finite index subgroups. Well, in any case, if you have an infinite simple group, this group is not retrievally finite because this group doesn't have non-trivial finite index subgroups, because each time you have one, then you have one that is normal, and you can have normal finite index subgroups. So here I should also mention that infinite simple groups are not retrievally finite. In any case, the question of whether a given group is retrievally finite is pretty hard. I mean, you have this small Sips criterion that depends on linearity, but linearity is hard to characterize. And probably the main question related to retrievable finiteness is about hyperbolic groups. So are all hyperbolic groups usually finite? And this question is complicated because now we know kind of examples of weird hyperbolic groups. So in particular, now we know that there are hyperbolic groups that are nonlinear. Yeah, and Konstantinos has some examples of these groups, and Konstantinos will give a mini course next week about an ASO representation. I don't know if he'll talk about these nonlinear groups, but in any case, probably he knows much more about this than me. But in any case, proving residual finiteness is a difficult question. In any case, we can construct some examples of residual finite groups from old ones. And the main point of residual finiteness maybe is that it is preserved under taking subgroups. So if G is a residually finite group, then the trivial group is intersection of finite index subgroups. And if we have a subgroup, then we just intersect these finite index subgroups with H. These new groups are finite index in H, and the intersection is still identity. So this implies that H is visually finite too. Also, some ways to construct, to have two operations. So we have direct product, which is not too complicated, but we also have free product. Okay, and this will be part of the exercises. So these two operations give finite, residual finiteness, as long as all these operations are finite, of course. And related to separability, what I want to tell you now is not a way to construct new groups, is kind of a criterion. So each time you have a separable subgroup, and we have a subgroup containing this group of finite index, then this new group is also separable. And how we use this criterion, in general, what we want to do is to prove that this H prime is separable. But for some reason, we have a criterion for H. And for some reason, we can make this procedure. So in this case, we can prove separability for H prime. And by the way, separability is not preserved under taking subgroup of finite index. In the case that if H prime is separable and we have this, then we can't conclude that H itself is separable. So we can go up, but we can't go down in terms of separability. Is there any question at this point before we continue? Okay, so let's continue with examples of separability. So what we can say, so the first examples are abelian groups. So finally generated subgroups of abelian, finally generated abelian groups are separable. Indeed, here we don't need finally generated. Well, we have this for free. All of them are finally generated. And we can change this and just impose the group to be nilpotent, but still finally generated. And we have similar results for interesting groups. So finally generated subgroups of free groups are separable. And this is a nice result. And I mean, by the end of this talk, we'll have enough tools to give a proof of this. I mean, following the Stalin's approach. Oh yeah, polycyclic groups have this property too. And I think among solvable subgroups, those that are polycyclic are exactly those that satisfy this property of all finally generated subgroups being separable. Well, but in any case, I mean, I usually omit that because in the cubulated world, we don't have polycyclic groups. I mean, all of them are virtually abelian. But yeah, that is true.
You said nilpotent, so.
Oh, yeah, sure. My bad. Okay, so finally generated subgroups of free groups are separable, and we have a similar result for surface groups, which is pretty nice. And I mean, this property is kind of strong, so we can put a name to this. So finally generated subgroups of G being separable. The definition of this is now called Bindler. And this LE comes from locally extended. And in particular, these groups are visually finite, but we have a lot of separable subgroups. I mean, you can construct finally generated subgroups for free, right? And at this point, you're wondering, okay, is this property true for any visually finite group? And the answer is no. Okay, so yesterday I told you if a property holds for any free abelian group and a property holds for any free group, then it should hold for any right angle Artin group. Okay, a counterexample of what I told you yesterday is given here because we have finite index subgroup. Sorry, we have finally generated subgroups of the product of two free groups that are not separable. And what is the reason for this? The point is that groups that are separable have a solution to the membership problem. And for product of free groups, we can construct groups for which we don't have a solution to that problem, which at the end reduces to having groups without solution for the word problem. And I think at this point, there are a lot of ways to group this, but the way I know this comes from the construction of Mihailova. In case you are interested.
Do we know if quasi-convex subgroups of hyperbolic groups are separable?
We don't know, and that is equivalent to all hyperbolic groups being residually finite.
It's equivalent to, sorry, to what?
I mean, if all quasi-convex subgroups of hyperbolic groups are separable, in particular, that implies that all hyperbolic groups are residually finite because the identity is quasi-convex, but it turns out to be equivalent. I mean, if all hyperbolic groups are residually finite, then we can prove that all quasi-convex subgroups are separable. I mean, for hyperbolic groups. So that is not known. Well, in any case, now I'll tell you the only effective criterion that I know for separability that works in full generality. I mean, we need some conditions, but in principle, we don't need extra assumptions for the group besides being residually finite. So you have two residually finite groups, and we have a group subgroup H that we want to prove is separable. The condition that we need is that this group is a retraction. So if there is a retraction, that means map R from B to H such that the restriction to H is the identity, then this implies that H is separable. Okay, and the proof is not at all tricky and it's kind of short, so I will leave this as an exercise. But in any case, just to point that we need to begin with that the groups are residually finite. I mean, and this is a strong condition, but in some contexts, we have residual finiteness, and we can promote residual finiteness to separability in case we have a retraction. So an immediate corollary of this, so suppose we have a right angular R group and that we believe that this group is residually finite, then what we can do is we can consider a subset of the generators, and we can do is we can kill all the generators that are not in this set, and that produces a homomorphism from G to, I mean, the subgroup generated by this T. So here we kill the generators that are not here. And the conclusion is from this is that this subgroup is separable. But in any case, I mean, this comes from this combinatorial structure. But in any case, we want to prove more because, I mean, if you have a lot of, I mean, if you want to have freedom in convex subgroups of right angular groups, I mean, we need some ways to produce more separability than just using this simple trick. And for that,
sorry, just so by the lemma and the comment you made above, virtual retracts are also separable. Is that?
Oh yes, virtual retracts are also separable. Yes. I mean, and this is the way in which we'll use this lemma in general. So virtual retractions are separable. And for that, we use somehow this version that if we go up to finite index, we still get something separable. Yeah, but yeah, I mean, in general, we'll use this version that virtual retractions are separable, as long as everything is visually finite. Okay, so to continue, we must go back to the cubulated world and to talk about special cube complexes. So now we are back to X being a cube complex, and we define this non-positivity curve cube complex to be special if the walls satisfy some specific conditions, or maybe better, they don't satisfy some really, really bad conditions. So the conditions that we want to satisfy for the walls are that the walls are embedded. That means that there are no self-crossings in this way. And also we want the walls to be two-sided. That means we don't have this kind of Mobius strip behavior. And from these two, we can get that the walls are, first of all, oriented. Or maybe orientable. That means we can draw some arrows here in a consistent way for the edges that are transverse to the walls. But in any case, we don't want two conditions. One is self-osculation. So this behavior is called self-osculation, and we don't want this to happen. But in this case, we must be careful that we are being careful with the orientation. So this this vertex is final for these two edges, or initial depending on the orientation. But if we have one of them being initial and the other being final, then this is fine. But in any case, this is a technicality. You can assume that this is what we don't want to happen. But we also want some property related to the interaction of two walls. So if two walls cross, then they won't osculate. So this is also forbidden. In any case, what is the moral of all of this, and a way to remember this is that for special cube complexes, these complexes are cat zero from the point of view of the walls. So this is the picture to have in mind, even though these complexes are not contractible. In any case, all of this is combinatorial, and this can be checked each time we have an example, which is finite at this. And examples of this, of course, are cat zero. So cat zero implies being special. Also, each time we have a special cube complex and we take a covering, that covering is also special. Also, we can check that graphs are special because, I mean, the walls are just points. But also the product of two graphs is special. Also another example that we should see are Salvetti complexes. Okay, and this example is relevant for all the theory, so this is part of the exercises. And also we can check that surfaces for the cubulation that I gave you, this cubulation is also special. So surfaces have special cubulations.
Products of special cube complexes are special as well, more generally, right? Isn't that?
Yeah, I'm pretty sure, yes. Okay, in any case, I'm not 100% sure, but I mean, this looks reasonable. well, so we have these special cube complexes with this nice behavior of walls, which might seem mysterious in any case. Okay, they are. Thanks, Macarena. So we leave with that. Great. Okay, so we have special cube complexes, but again, for some reasons of the theory, which you might consider, which is, I mean, a problem of the theory, but I think this is a way to include nice groups that are non-special, but are still nice enough. We need to work with virtually special cube complexes. So a cube complex is virtually special if we have a finite cover that is special. We have a cover is finite that is special. And we want to work with groups too. So if you have a cubulated group, this cubulated group could be virtually special if there is a finite index subgroup such that this action is now free and that the quotient is special. Okay, and here I must do some remarks. So from our definition of cubulated group, we are in principle assuming that this quotient is always compact. I mean, if we take a finite index subgroup, this quotient is still compact. So in literature, you might see this as being virtually co-compact special. And a general definition is that a group is virtually special if it is virtually the fundamental group of a special cube complex that is not necessarily compact. Well, but in any case, I think this definition is still nice enough because we are working with cubulated groups for this mini course, so this is fine. And what would you say? Okay, so we have this combinatorial definition for special cube complexes that is kind of tricky, but there's a good reason for this definition, or maybe at least there is a nice equivalence. And for this equivalence, I should tell you about the crossing graph. So what is the crossing graph? So we start with a, let's say, finite cube complex, and we want to codify the information of the intersection of walls. So we construct this crossing graph with vertices being the walls of X, and edges are given by crossing walls. So crossing means always this. Oh, sorry. Where is this one? Somewhere around here. Okay, so vertices given by walls, edges given by crossing. Crossing was this. And as an example, in the cubulation for the surface that I gave you, we have all these walls that now are edges in the crossing graph. And what we do, we just check the crossings. And if we check the crossings, we should get something like this. So the green one intersects 3 walls and have this one. Okay, so this is the crossing graph. And why is the crossing graph useful? Is because we can construct a cubical map into a Salvetti complex. So there is a cubical map from X into Salvetti complex of the crossing graph. Oh, this is not what I wanted. So this is Salvetti of crossing graph. And how how we do this? Okay, we send, this complex has a single vertex, so we send every vertex to this single one. And then what we do is, if we have a wall here, then this wall is transferred to a given set of edges. And what we do, we send all these edges to the loop corresponding to the wall in the crossing graph. So we have a map in the one skeleton, and then we just extend to the higher skeleton. But even though this map is in general not well behaved, and what special means exactly that this map is well behaved. So actually, this is a theorem, but this is actually just checking everything. So a complex is special if and only if this cubical map is a local isometry. Is pretty nice. And at the level of fundamental group, this implies that we get an embedding from the fundamental group of this special cube complex into the fundamental group of the Salvetti complex. That means we get an embedding into a right-angled Argand group. And this is one of the reasons of why this theory is interesting. We come from, we start with just a combinatorial structure for a cube complex, and we end up with an embedding of the fundamental group into a right-angled Argand group. So what you should remember from this talk is at least this. So special groups embed into graphs. This is something you should remember. And consequences of this, of course, if we still believe that racks are visually finite, we'll see that in a few minutes. But with that being said, we know that virtually special groups are visually finite. So, checking that a group is virtually special is somehow a sufficient condition for a group to be visually finite, which is nice in terms that this depends on information that is not as strong as, for example, testing linearity. That depends on another structure, which is more combinatorial, and that in some cases we can check. Another consequence is that if we compose this local isometry with a local isometry given by a convex subgroup, we can get that convex subgroups or virtually special groups are also virtually special. So in all these kind of category of cubulated groups and convex subgroups, we have this subcategory of virtually special groups in which this convex embedding implies being virtually special for the subgroups. So all of this is kind of consistent. But we want to get more information. We don't want to only get visual finiteness. We want to get separability of subgroups. And this is the content of the canonical completion and retraction. So
sorry.
Yeah.
I'm sorry. I don't see how the second how is the second bullet point a corollary of what is it?
Okay, so we get a convex. Well, maybe at this point this is not a corollary of what we have. Maybe we need Half-Long and Weiss criterion that we'll see in a few minutes. But what I can say, maybe you can, the point is that you can consider as definition of being virtually special is that you are a convex subgroup of a right-angular group.
Okay.
Okay, so you're right, maybe this is not a corollary, but at the end it won't matter if this is a corollary or not. We'll live with this. We'll have this at the end. Yeah, thank you. Okay, so about the canonical completion and reduction, this is a pretty nice construction, and in the paper of Halloran and Weiss, this is the construction is transparent and it's not that long. I mean, we just need to check a few things, but it's actually not bad. But I don't have time to describe the whole construction. Instead, I'd like to tell you, I mean, how this works and what can we get from this. So the situation is like this. You have a special Q complex X that in practice, it doesn't have to be compact, but we need this Y to be compact, and we need a local isometry from Y to X. And the situation is similar to what we have here. You can imagine that this is, for example, a Salveri complex. So we're in a situation like this, and what you can get from this is a finite cover. We call CYX, and this is the canonical completion. And this completion is not a completion for X, this is a completion for Y, because we get also an embedding, also local isometry, from Y into this completion. So we get this, so we promote this local isometry to an embedding in this finite cover, and moreover, we get a retraction R from C by X to Y. And retraction means that when this composition, if we go up first and then we come back to the retraction, this composition is the identity. And this is pretty nice. And the reason of why this works, I mean, we need this complex to be special, but the point is that we construct this retraction combinatorially. And the point is that from the combinatorics of this construction, since these maps are by one injective, we get something useful at the level of fundamental groups. So at the level of fundamental groups, what we get a retraction R from the fundamental group of the this canonical completion to the fundamental group of Y. Yes, I think there's a question in the chat. Okay, so about the completion, I don't think this completion is unique in terms of all of this, but the construction is kind of canonical. Well, I don't know in what sense saying this is canonical without going into the details, but everything I have to tell you is that, I mean, everything I can tell you is that this construction is functorial. I mean, maybe this is not unique, but this is functorial. Maybe in the same way as we can construct canonical k-pi1s for groups, even though they are not unique, but we can construct one for each of them such that all these maps are actually, I mean, we get a subcategory on k-pi1s. So this construction, I shouldn't say this is canonical in terms of this, I mean, unique in terms of these properties, but we live believing that this is unique. I mean, we don't try to get new construction from this. Okay, so what happens at the level of fundamental groups? We get a retraction, and that means that since if this group is residually finite, then the fundamental group here will be residually finite too. That means that we can apply the retraction criterion and conclude that pi1 of Y is a virtual retraction of pi1 of X. That means this will be separable as long as this group is separable, which will be the case because it is special. As a corollary of half of this construction, that means just of the completion, is that virtually special groups are residually finite. So that means that for any element which is non-trivial, we can produce a finite index subgroup not containing it. So the goal is to get a prime of finite index such that G is not in this subgroup. And what we do is as follows. So first we get, by definition, a finite index subgroup that is virtually, that gives us special cover. So this cover is special. So this is our quotient, and we can assume that this G is represented by a loop here. By a loop gamma. And what we'll do is we want to, in a finite G cover, to get a non-closed loop as a lifting. I mean, a non-closed path as lifting. And the first place to look at is the universal cover, of course. So we lift M hat in the universal cover, which is X. So this is X. And here we have our lifting M hat. And now we use the cubical structure. So first we consider a convex finite subcomplex containing the lifting. That means we consider this K, and this K always exists because, I mean, the lifting is compact in the universal cover. And the situation is like this. We have K, now an embedding in X, and now this goes to this special quotient. And this composition gives a local isometry. And now it doesn't matter what is the topology of this complex. The point is that this is special. And we can construct this canonical completion. And for this canonical completion, what we get is that now K embeds in this canonical completion. And what this means that now this non-closed path, which is a lifting of gamma, will go to another lifting of gamma here that is again non-closed. So that means that G is not an element in the fundamental group of this canonical completion that we can call G prime, which is finite index. So here we didn't use the reduction, but we used the canonical completion, and this implies implies visual finiteness just from combinatorial information and this construct. And this uses that the complex are special. In any case, as a corollary of this, what we get is that convex subgroups are now separable by using this virtual retraction criterion. So convex subgroups of virtually special groups are separable. Okay, and this is another thing that you should remember. Maybe not that convex subgroups themselves are separable, but that for virtually special groups, we have a bunch of subgroups that are separable. So in particular, for hyperbolic groups that are cubulated, convexity is same as quasi-convexity. So in case of the question, I mean, related to the question of Abdullah a few minutes ago, we get that for cubulated hyperbolic groups, once we know that they are virtually special, quasi-convex subgroups are separable. In any case, if we go further and we get, and we use this functoriality of the canonical completion, we can get something for double cosets. So double cosets of convex subgroups. Of virtually special groups are separable. And this uses the functoriality of the canonical completion retraction. And the only thing I have to say here, I mean, why we care about double cosets is because the only criterion that I know for virtual specialness for cubulated groups depends on double cosets. So we have this theorem of Handel and Weiss, in which we start with a cubulated group, and we want to know if this cubulated group is virtually special, but not in terms of checking. I mean, you don't want to check every finite cover and check that the cover is special. So instead, what we do is we check that the walls are separable. I mean, the wall stabilizers are separable for any wall. And we check that the double coset given by wall stabilizer is separable. For intersecting walls. And everything I have to say is that, okay, we saw some tricks for separability, but separability of double cosets is a painful process. Usually, I mean, first we already need separability of subgroups to get separability of double cosets, but this is usually a really technical problem. And probably half of, I mean, papers that prove virtual specialness, the problem is usually to get this. That's why this proposition is kind of meaningful. But in any case, why we care about this? So this is to get rid of self or inter oscillation in finite covers. Well, in any case, this is the only criterion for virtual specialness without extra conditions on the group. And I'd like to spend my last minute with some questions about all of this. So the first question is related to virtual specialness because this depends on accumulation, but maybe it doesn't depend on accumulation in the sense that if Dx is virtually special and Y is another accumulation, of G is YG virtually special? Is this
known for certain cases? Or
yes, yes. I mean, I know this is true for virtual abelian groups and for hyperbolic groups, but I don't even know if this is true for right-angled Arden groups. I mean, for F2 cross F2, I don't know if that is true. So I think this is an interesting question, and also an interesting question related to that group that is non-Lerf. Are finally presented subgroups of virtually special groups separable? Okay, so this example of non-separable subgroup inside the product of two groups is not finally presented. So maybe the point is that we are not looking at the right subclass of groups to get separability. But in any case, I mean, I don't have any insight of what to do for these two questions. These are just in case you're interested. Okay, so I'm on time. So next time we'll play with Cubulated. hyperbolic groups.